Hello, everyone. Welcome back. It's been a little while. I feel like I owe you all an apology for that. Um, my Surface's storage that I use for these little videos got filled, and I needed to get some more storage. And this turned out to be quite an adventure. So I'm sorry for the delay, all six of you who are so who pay attention to this and care. Um, but I'm ready to pick up where we left off. So I wanted to start the next section. That's 2.3 of Kashiwara and Schapira, which is about con extensions. And this is a concept that evaded me for a little while, and I don't claim to have fully grokked it yet, but I'm going to do my best to explicate what I learned from this section over this video, probably at least one more video, maybe even one more after that, because, well, two reasons. First is that there's a handful of really good examples, not just like good in the theoretically enlightening sense, but good in the practically enlightening sense. There's a rich source of computations that can be done, and we want to do some of those. Um, but another reason is that there is a slogan that I've heard for a very long time um, that says that every concept is a con extension. And I don't really understand that yet completely, although I'm getting there. And so that would be a thing that I would really like to understand and be able to explain um, in a video like this. Um, so I don't know. We're just gonna get into it for today, and we'll see how far we get. But my hope is that by the time that I'm done thinking about everything in this chapter, I'll really have understood what this means. So if you haven't seen a con extension before, then everything I've said hopefully is something that kind of grabs your attention and has your interest. But maybe it's time I actually start saying what these things are about. So we start, as always, with these sections with the new definition, which is as follows. We have two categories, I and J, and we regard these guys, I'll remind you, these are sort of what they call indexing categories, or we think of them as sort of like sets. There's small categories, there's a bunch of course, morphisms on the objects, and we want to think about, e.g. limits that are indexed by these things, or other constructions, as we're about to see. And we have another category, which is C. And now, suppose we have some functor, phi j to I. Then what we can do is construct what you would call the precomposition or the pullback. I know that might be a bit confusing because the pullback, as the category theorists talk about it, is something different, but the rest of mathematics calls precomposition the pullback, which is denoted with an upper star. And this is a functor between two functor categories. It takes functors in IC, or functors in the functor category from I to C, and spits out functors in the functor category from J to C. And the idea is, of course, if I have something from I to C, then I can get something from J to C by just first applying phi and then doing whatever that functor was. A remark is off the bat, I know we're like just getting started, but Kashiwara and Schapira denote this with a lower star, and I think that that's an unusual piece of notation. In fact, in the Discord we went as far as to call it cursed notation. So I'm going to use the upper star notation, like whenever I can get away with it. Maybe if it turns out later in the book that I should use the lower star notation or it just gets too confusing, then I might go back and copy Kashiwara and Schapira later. But for now, I want to use notation that's consistent with the usage in the rest of mathematics. And so what this does is, of course, it's defined by phi star of alpha. It's just alpha composed with phi. That's what I just said. Now, but let me actually finish the definition. If this functor, if phi star, has a left adjoint, then we call the adjoint phi dagger. I know my dagger looks sort of like a T, but I can't write in LaTeX. And if it has a right adjoint, then we call it phi double dagger, like so. And again, Kashiwara and Schapira, they have the upper notation for the adjoints because they have the lower star in the upper adjoints, and it just sort of makes sense to me to put everything down in the bottom. Whenever you have an adjoint triple, usually like one of the three, like the middle one is up or down, and then the other two are the other way. So I'm just trying to keep everything consistent, and that means sort of reversing everything. And I'm sorry if that turns everyone on their head, but I got to keep this straight somehow. Okay, and then of course, okay. Oh, so these are our adjunctions. So if it has a left adjoint, then it is the right. It is the right adjoint itself, and so we call that the right Kahn extension. And Kashiwara and Schapira don't say that anywhere in this section, which was part of the reason that this took a while to understand, because I was asking myself, like, what's okay? So like I read the section, I understand all the constructions, and I think I understand the proofs, but where are the Kahn extensions? Well, after reading in Emily Reel's book, which is of course completely invaluable, maybe I point you to her. I was able to make some progress, and the book is called Categories in Context. Okay, so when we have this kind of setup, then you might recall we have the unit and co-unit. We have eta, which is a map from the identity functor to this adjoint composition. And then there's epsilon, which goes the other way, and we have this guy now with phi double dagger to the identity. The unit and co-unit. And what I want you to notice is that these two are adjoints to the pullback, but not to each other. So maybe a cautionary remark is that phi dagger and double dagger both go in the same direction. So they have no relation to each other, at least in general. I didn't see any examples where they had any relation to each other. But the way that you should visualize these, what you should think about is I have this functor, just sort of drawing the diagram from what I said in the definition, is you have this map from j to I, and then maybe some functor, beta, and then these adjoints, if they exist, look like this. And this will be either phi dagger or double dagger, depending on which of the pair that I get. Something else that's important about these guys is that while they're not related to each other as functors, like I don't know, I guess maybe I do know a formula that connects them. I guess I'm just sort of putting this all together now. Is that we know that if I take the opposite category of a functor category, then that's the same thing as the functor category between the opposites. And this allows us to sort of deduce one of these from the other, which I guess I could use to make a formula if I tried a little bit. I haven't done this, but I encourage you to do this if it seems useful to you guys, which is that I can make a diagram like so. This should be I, C, op. Everything on here is on the with the opposites on the outside, and then we have these isomorphisms that we just said, where now the opposites go on the inside. I op, C op. And these guys, we just said these are equivalences, and then over here we have the opposite morphisms to these guys. And so they're related by this diagram. So whether I first apply the equivalence or do the adjoint or the other way around, that determines which are the ones that I want. Okay, so something that's important about this also, and we're starting to notice this in the book itself, is that it's very annoying to talk about whether or not constructions exist. The sort of Yoneda philosophy that we've been learning, or at least that I've been really getting out of this, is that it's better instead to pass to some larger category where everything always exists, and then ask when the functors that we deal with in this more abstract functor category are representable. And so if we do that, then we can sort of take the Yoneda viewpoint or the Yoneda philosophy, and then we can make a new definition, which is instead of saying if there is a left adjoint or a right adjoint, then what we do is we take the functor, which sends alpha to Hom, maybe I should be clear and write everything out, Hom in the functor category from J to C, beta phi star alpha. So if this is representable, if this is representable, its representative is phi lower dagger. And similarly, alpha hum, and eventually I'll stop writing this, but the argument goes over here this time instead. Then the representative is phi double dagger. Okay, so the now how do I want to keep going? I suppose that there's some sort of set theoretic issue now that I'm just sort of having myself to think about this. But I don't want to think about it. Like somehow everything in sight is supposed to be done with respect to some large universe, and I kind of just don't want to worry about it. What I want to do in this video is show probably 2 or maybe 3 examples now that sort of explain or illustrate what's going on with conic extensions. At least some toy examples, and then probably that'll be long enough, and then next time we'll do some more interesting examples. So let's get started and see how far we get. So we have some toy examples. For the first toy example, I want to look at probably the simplest possible functor that I can think of for indexing sets. Let's take the functor from 2 to 1. This is just a constant functor. And then let's send 2 to set. Oh, I didn't say what exactly the category 2 is. 2, because with 1, it's sort of obvious what I could mean by that, because there's only one. There's only sort of one canonical category with a single object, although there are lots of examples of one object categories. 2 here means the discrete category with 2 objects. So in other words, no morphisms other than the identity ones. And so now this vertical arrow, what does this do? Well, what is a functor out of a 2 object category? Well, it just picks out 2 objects. There's no morphisms. So this vertical arrow is just giving us an ordered pair of sets. That's all such a choice does. Excuse me. All such a choice does. Whereas the horizontal map, well, that's just a constant functor. Okay, so on the other hand, if I want to produce a functor that goes this way, this is a functor which then also picks out a single set. And now what I need to do in order to construct such an adjunction is satisfy certain formulas. And if I label some of these guys, then what we'll see is that the construction that I need is hum in now set from maybe we'll call these functors alpha and beta. And then here we end up in the product category, set cross set. Like so. And if this is a little bit mysterious, then don't be alarmed. Just maybe have yourself a quick pause of the video and just straighten this out. I'm sort of abusing a little bit of notation here. What I'm doing is identifying the category of functors from 1 to set with just set itself. Because, well, there's only a single thing, and just it's this sort of usual mantra where I identify a functor with its image or a function with its image, but I'm doing the same thing with a functor on a single object category. Now, on the other hand, the catch is that the hum in the product category, well, that's just the product of hums in the individual categories, and both of these are sets. And morphisms in a product category are component-wise. And hum is contravariant. So what I expect then is that in order to make this this bijection possible, then what has to happen is I need to have phi dagger of beta has to be the functor which sends us to the coproduct phi dagger of beta 1 has to be, how do I write this? I should write maybe equals. I'm just a little bit worried about equals versus isomorphic. The coproduct of these two guys. Like so. And if I try to do the same game with phi double dagger, well then the equation that I get, instead of having the adjoint thing that I'm interested in the first argument, I'll have it in the second argument. And in that case, what happens is Hom is now covariant. And so in that case, then what I get is the product. I guess this should really be isomorphic because nothing really, everything here is only like so. Okay, and so there's an extent to which this is very general, and sort of later on in this topic of conic extensions, we're going to elaborate on that. But this sort of stands to illustrate the idea that, at least we have the potential here, that limits and colimits are going to become examples of conic extensions. And we've at least seen this now in a baby case, but later on we're going to do this in some more detail. Let me show you another example. Maybe this is more of a non-example, but it's a non-example which is illustrative of what's going on. And this is coming from just group theory. And in group theory, well, first, a quick reminder is every group is a category in a maybe not completely obvious, but simple way. A group is a one-object category with morphisms indexed by the group elements, and they're all isomorphisms because every group element has an inverse. And so when I want to play this game with groups, then it's very easy to translate all of the notions that we need into group theoretic language because, well, then what is a functor but it's just a group homomorphism? And so the question about extending a group homomorphism from one group to another is a question that we can be regarded as a question about conic extensions. And so in this case, what I need to do then is find some functors to make some diagram commute. This amounts to transferring or extending group homs from one group to another. And when we want to do this, well, I guess one possible concern is that, like, typically when I think about extending a group homomorphism, I think of it as something that I do from a subgroup to a whole group. And we talked about how to make subgroups sort of categorical in one of the very first videos. But the question about conic extensions makes sense even if the homomorphism isn't injective. It's really more of a transfer of homomorphism maybe rather than an extension. But it's sort of the same story either way. In the example I want to show you, I am going to work with an actual subgroup. And we're going to see that it's not always possible to do this when you insist on some further structure. So what we do is we'll just think of the alternating group as our example. We take the group A4. And I hope that everybody knows this, but A4 is just the subgroup of the group of all permutations on 4 elements that involve an even number of transpositions. And A4 has a normal subgroup, which is the Klein 4 group. I don't really need to write this lower line because it's no equals. But that's usually written as V4. And V4 is just the double transpositions. At least that's the way it sits in A4. Now, what is the quotient of A4 mod V4? Well, this is easy to identify because A4 has order 12 and V4 has order 4. So then the quotient has order 3. So it must be isomorphic to Z mod 3Z. Okay, so this means we have a surjective map from A4 to Z mod 3Z. That looks like this. And now A4 sits inside S4. There's an inclusion that goes like this, which just includes, and maybe I call this guy pi. And now we can ask the question, is it possible to extend this surjection to z mod 3z from A4 to S4? And what we're going to see is that the answer is no. The way that you see this is that we look at the index of A4 inside S4. And this is 2, as I hope everybody knows, because A4 is the even permutations. And so if this was possible, we would have to have a normal subgroup in S4 of order 8. So there would have to be a G inside S4. Order of G is 8. But S4, the subgroup theory of S4 is very simple. What are the normal subgroups of S4? Well, there's A4, and then there's also V4. The same copy of V4 also lives in S4, and it's also normal. But that's actually it. This is an exhaustive list of all the normal subgroups. At least, if that's not true, then I'll have to give back my degree. So someone will have to call Stony Brook. Okay, so anyway, the point is that neither of these have order 8. And so it's not possible to find this extension. And maybe just to give a little bit of insight into what's going on here is, well, we could talk about homological algebra. We'll do that later. But let's just think about this on the just sort of purely group theoretic side. If I wanted to understand the group of natural transformations between these maps, then what I would do is I would have to look at maps. Maybe I'll call map alpha S4 to Z mod 3Z. And the question is, what are such maps? Well, let's have a think about that. We know that the symmetric group is generated by 2 elements. In particular, it's generated by a transposition, and it's generated by a 4 cycle in this case, but an n cycle in general. And the image of those things would then determine everything in the group. The problem is that a transposition cannot map into Z mod 3Z in any good way because it's order 2 and Z mod 3Z is order 3, and those are coprime, so that can't go anywhere. And similarly, a 4 cycle can't go anywhere either. So actually, this is 0. So what's happening on the sort of maybe category theoretic level is that for every such alpha, the functor that I'm looking at, the Hom functor, sends this alpha is 0. So if this representative functor existed, it would have to be the 0 functor, but that doesn't make the diagram commute. So there is no such representative. So in other words, this could be represented, but it doesn't satisfy the diagram. So there's no con extension. So I haven't really quite figured out how to think about this yet. But it's sort of a thing that we've seen before, or at least I've seen before in math in a lot of places, where like you have some theoretical description of something, and from this you glean what are basically equations that have to be satisfied. This is what we did in the first example, where we said if a set exists with these properties, it has to satisfy these equations. From those equations, we deduce the order of the set. That's all you have to do to know to set up the isomorphism. So in both the first and the second cases, we used the structures of the categories at hand and the adjunction equation to actually extract from them some properties that have to be satisfied in order for these extensions to exist. And then we either use that to produce the set, as we did in the first case, or in the second case, we saw those equations have no solutions. And this is the kind of thing that we actually do like a lot. Like for example, I've done this all the time in algebraic geometry. Like you have a variety, like let's say you have a projective variety. You want to know like is it singular or not. So you take the derivative matrix and then you want to figure out like what conditions make the rank change. And then that gives you some equations that you can then solve, and then you have to plug those back into the original variety in order to actually know that they're points on the variety. And like oftentimes the only point that makes the variety singular is the point 0, 0, however many zeros there are. That's not a point of projective space. And so you would, in that case, similarly conclude that there are no such points and that the variety is smooth. Now, of course, in projective geometry, that's what you want. But it's sort of the same idea of like having some abstract condition, like the rank of the Jacobian matrix. This is going to be sort of phrased, and if you look in like Hartshorne or so, it's like defined in some very intrinsic way, and then from this you extract some concrete, tangible equation, and then you go back and you check like do the solutions of the concrete thing actually satisfy this theoretical property, um, and if the answer is no, then there is no such thing, and that's sort of what we've been doing here. Okay, this video is already almost a half an hour long, so I think I'm going to end here. Let me just say a few words about where I want to go next. Of course, more examples, but in order to say what the examples are going to be, I worked out, so first off, a formula for computing Conn extensions. And these formulas come with some hypotheses, but as we've seen, everything we want to do takes place in some functor category, and functor categories, like into set, for example, are always complete, co-complete, yada yada. And so for lots of practical applications, these hypotheses will be satisfied. Then I worked out an exercise from Kashiwara and Schapira that I'll share with you, which implies adjunctions are examples. And I don't know if any of you guys are still doing any of the exercises, but if you are, then maybe you also did this one. And then an example from topology that I have come to appreciate is simplicial sets. Really, this is, I guess, more from homotopy theory, because simplicial sets a little bit more general. And the pair of functors is singularization and geometric realization. And I'll tell you guys what those are, because I don't expect you guys to know anything about these other branches of math. But my hope is that after seeing these, among some other examples, like, once we have adjunctions, then, for example, like, that includes things like Hammond tensor. And these are also an example. Singularization and geometric realization are also an example. So maybe I include tensor. Maybe this is really better off set as 2.5, because it's sort of a consequence of the exercise, which in turn is a consequence of the formula. So really what we're going to do in the next video is understand this formula, and then from here produce a bunch of more interesting, or maybe less toyish and sort of more sophisticated examples. Okay, it's been great to be back. I'm excited to continue learning and to continue sharing with you guys what I learned, and I'm looking forward to seeing you guys in more or less a week. Take it easy, everyone. See you soon.